So Rohit Budhiraja is currently an associate professor at IIT Kanpur in the EE department. So he is leading an effort from IIT Kanpur to design an Indian 5G testbed. Before joining IIT Kanpur, he has actually worked for two startups where he designed both hardware and software algorithms from scratch for physical layer processing of WiMAX and LTE-based cellular systems. So Rohit, thank you for agreeing to talk, and I invite you to start your talk.
Thank you. Thank you, Rajesh. So I'll share my screen. Is it visible?
Yes, Rohit, go ahead. Yeah.
Okay. Thank you for the nice introduction, Rajesh. And I'll straight away start with the major goals of this 5G testbed. And so you can see that it is to encourage existing telecom product startups and encourage new startups and to multiply R&D capability to develop 5G solutions for Indian markets. So this will hugely enhance capacity in 5G technology skills. So, and another goal of this 5G testbed is to develop India-specific solutions. So there is something called low mobility large cell scenario, which has recently been accepted by ITU for as one of the key evaluation for any 5G technology. Another similar application, smart city applications. Plus, it should help India in increase participation in global forums like 3GPP, ITU, IEEE to present test results for Indian use cases and provide Indian government with correct technical information. So this should enable researchers, academicians, industry, Indian industry to provide this kind of information to the government. And it was first proposed by Professor Ray Balraj. And it's a 3-year project funded by a Department of Telecommunication. And the objective is to build from scratch and demonstrate an end-to-end 5G testbed. So these are the partner institutions in this testbed, and you can see that most of the premier Indian institutions are involved. Plus, there is a Center of Excellence in Wireless Technology, which is operating out of Chennai, and there is an organization, Samir. So these are the institutions. All of them are government-funded institutions. So currently, there are like 40 investigators, senior members, senior researcher, faculty members, and 260 employees. Even more than that, there's a little old number. And we are like continuously engaging with Indian telecom startups for various subsystems. So even before so this is how the testbed locations will be. So it will these testbeds in some form will be located at all these IITs. So these are the locations, and so I'll give you a whirlwind tour of what we are designing. And what is the thought process? What is the philosophy of designing this testbed? So if you look at a cellular system layout, there is a base station, and all these cellular systems reuse the frequencies in all the cells. So what this typically leads to is this intercell interference, and that has been typically a major bottleneck till 4G system, because this since we are using the same frequency in all the cells, so these two cells interfere. And now, so massive MIMO helped us in tackling this interference. And if we use large number of antennas at the base station, so one can show that, and it's well known that the base station can form very sharp beams toward these users, and these beams then do not cause this intercell interference, which has typically been the case till the 4G systems. So yes, large number of antennas help in forming a pointing beam toward the user. So this is a key differentiator of a 4G system from 5G systems. So and we are also designing this kind of testbed. That's why I thought I'll first touch upon this. We are building a massive MIMO testbed, which has 64 antennas for sub-6 GHz system. I'll take you through all that. But this is something what we are doing, okay? So this is how the architecture of the testbed, which is being designed, looks like. So that will be this, let's say there is the cell site, first cell site, and these are the users. So what we have is the base station is architected such that there are these devices, remote radio heads, and these are like, they do a little bit of physical layer processing. And each remote radio head has like 120-degree sector. So there are 3 such remote radio head, and they are like each remote radio head is 64 antenna, and they are like primarily used for radiating the signals and doing a little bit of physical layer processing. And these remote radio heads are connected to the baseband unit. And inside, I'll describe what we mean by baseband unit. Okay, so this each remote radio head is connected to a baseband card. So there will be 3 such baseband cards which will be required for controlling or for doing the signal processing for a complete cell site. Okay, so and then on the back side, it's connected. The baseband unit is connected to a 5G core through a backhaul fiber, and this is the front haul fiber. So similarly, there will be the cell site 2, second cell site. It will be similarly connected to a set of 3 baseband cards. There will be another cell site, which will be again connected to a set of 3 similar cards. So all of them, of course, are connected to the 5G core. And this is how this test bed will look like. This is the architecture. We call this as cloud because the complete processing, the complete intelligence is sitting somewhere here. Okay, and so this is how the layout will be. So one baseband unit, the way we are architecting is it can control three such cell site, each cell site with 3 remote radio heads, and so in total of 9 remote radio head, one baseband unit can control. Okay, so let's go a little deeper into the base station architecture, which is called G-Node B. So this is the overall layout. Now I'm focusing on this part of this test bed, which is called G-Node B. So the way we are architecting is, as I showed you, that there is a remote radio head, there are these baseband units, and they are connected over optical links. And these optical links are, the way we are designing is, we'll use ORAN interface, which is an open RAN interface for communication between the baseband unit and the remote radio head. So what this G-Node B implements is the L2, L3, and the physical layer and the RF layer components. And so this is, so a remote radio head has RF and antennas, and this baseband unit does the complete L2, L3 processing. So, and then this baseband units are maintained at a single location. That's how the cloud radio test bed has been architected. And if you look at it, so if you look at the protocol stack, okay, so the way this ORAN splits is it gives multiple options, and there are these you can so what the way this software can be split is like, just to give you an example, that that remote radio head could be doing only the RF processing, and the rest of the processing has to be done by the BBU. Okay, so this split is called split 8, and then then you can take the split further up. Okay, so this called, and then there is a split 7.1, 7.2, 7.3. So there are these, you can RF can do this, remote radio head can do process lower 5. Okay, some part of the physical layer chain it can process. So these multiple options are there, and so what we are looking at is this split 7.2, and the way it looks like is that that the baseband unit will this split 7.2 is is this is the hi-fi, and this is the rest of the chain, rest of the protocol stack. So this processing is done by the baseband unit, okay, and then the rest of the processing, which is, if you look at it here, this is the split 7-2. So the rest of the processing, which is beamforming, resource element mapping, and the RF front end antenna, everything sits at the remote radio head. So that's how we have architected it. That if you look at the baseband unit, so it needs to process, it needs to do the processing for all these stacks. Okay, so which is basically L2, L3, and then the hi-fi, and remote radio head is responsible for processing of the lower phi, and then RF processing and the antennas. So this is the typical, this is the architecture, the software architecture we have used, and then we have architected the processing for remote radio head and baseband unit accordingly. So now I'll show you and give you a brief overview of how RRH, this is remote radio head, is architected. So if you look at it, as I said, we are designing a massive MIMO base station. So it has 64 antennas. Okay, so you look at it. This is these are the antennas, and this is basically each such board. Okay, has, if this is the block diagram. So each such board has 16 RF chains. So total of 4 RF chains. Okay. So this is what you see, and there are these such 4. Each such board has 16 RF chains, so there are like 4 such boards. So 64 antennas, and the data from all these boards, all these is taken to the data aggregator board, which is the one you see at the bottom. Okay, so so there will be like 5. So the remote radio head has 5 such FPGA boards, okay, along with the antennas. So each board has 16 RF transceivers plus ADC DACs and 1 FPGA to do a little bit of the processing for the lower phi. Okay, and then after this processing, this data is taken to the BBU when it is remote radio head is receiving, or it is taken back to the FPGA when the remote radio head is transmitted. Okay, so look at the complexity. So massive, these are the features. Massive MIMO with 64 antennas. Each antenna is connected to separate RF chains. It's a fully digital remote radio head, because we are because we are focusing on, we are talking about sub 6 gigahertz. We have designed for millimeter wave also, and I'll briefly tell you about that. But in this slide, this is the fully digital architecture. And now the way why one can ask this question, and why do we have 4 such boards? Because single FPGA cannot handle cannot be interfaced to 64 ADCs and DACs. So we had to split these interconnections across 4 FPGAs and 4 boards consequently. And this interface which we see is the 25 gigabit optical Ethernet interface, which is connected to the baseband unit. Okay, so this is this design and this test, the project started in 2018, and you see that this is a working remote radio head, which is for the sub 6 gigahertz, and you see 64 TX RX, 1.5 watt per antenna. TDD, we are designing it for TDD, and like it can handle 100 megahertz of, it can process 100 megahertz of bandwidth, and it will operate around 3.5 gigahertz. And these are some of the mechanical features. That this is the weight. We have done extensive calculations on the so that we can have a reasonable weight, because it needs to be like taken. It has to be installed on a tower, and technician should be able to carry it on his back, and so the weight has to be like within the constraints. Okay, so this is, as I said, we have designed this remote radio head for a millimeter wave system also, and this is basically it can handle 400 megahertz of bandwidth, 28 gigahertz. It will operate at 28 gigahertz. and it has 4 RF chains and 64 antenna phased array system. Okay. Now, so this was about remote radio head, and I'll tell you briefly how we have designed the baseband unit. Okay. So as I said, baseband unit is the intelligence is the part of the base station where the complete intelligence resides, and it needs to do it does processing for the hi-fi, okay, and which needs to do a lot of data crunching at very high, extremely high clock rates. L2, L3 also it needs to process. So the data for L2, L3, so which is basically packet-based processing and requires a lot of decision making. So the way we have architected this baseband unit is that it will be based on the Xeon server. Xeon server will do this L2, L3 processing, and the baseband card, which is basically requires extremely high data crunching rates at extremely high clock rates. So we have designed, this card has been designed in-house to take care of these this extremely high data requirements. And as I said, this does processing for hi-fi, and these are the typical functions which the hi-fi does. And Xeon server, this is RRC PDCP, basically L2 L3 processing. Okay, and the way it is architected is I've blown up this card, and the way it is architected is that these FPGAs will share the processing, okay, for the 100 megahertz or for 400 megahertz. This baseband unit does not change whether the remote radio head, we have to design this baseband unit such that it can handle the processing for both 100 megahertz and 400 megahertz of bandwidth. Okay, so that's how we have architected it. And so it is, the baseband card is connected to Xeon server using a PCI link. And on the front hall, we need this front hall to connect this baseband unit to the remote radio head. And that, as I said, is this 25 gigabits per second optical link. Okay, so this is a pictorial view. I'll show you the real, how it in reality also looks like. So this is the PCI compliant baseband card. And you see that a lot of paraphernalia sitting over here, and a lot of thermal simulations to make sure that the temperature remains within control. So all that is done completely in the institutes here. So in the beginning of this presentation, I mentioned that each baseband unit, which is basically a server blade, and each such server blade can handle these 9 baseband cards. Okay, and they're connected on this motherboard sitting over here. So each baseband unit can handle 9 cell sites. Okay, for each cell site we need 3 baseband cards. Okay, so this is the baseband unit. And this, if we want to, so of course we can have multiple cell sites more than which can be more than 3. So we keep buying these server blades and keep installing them here. Okay, the server rack. So that's how it is. That was the architecture, but that's how this card looks. So you look at the different views of this cards, and this is a server which we have inside the labs here. And it was designed here. It is up and running. So it's like the form factor is like Tesla NVIDIA card, and these are the like interfaces which with the technical interfaces for the L2 L3. So L2 L3 sits in the server. The physical layer sits in these cards, and the way these L2 L3 interacts with the PHY is through FAPI interface. These are well-known open interfaces, and we are also using them. And we are also designing the user equipment. So this is a snapshot of the user equipment. Okay, the 2 antenna user equipment. So basically a mobile which can radiate at 23 dB. And all these institutes have state-of-the-art labs. So you see this is all these labs were set across multiple institutes 2 years ago. Okay, so so this is how the testbed is architected, and I thought I'll show you some of the challenges which we have faced while designing these hardware, the software from scratch. And so the way we do everything in-house, and I just so if we in order to design the hardware, so we do the PCB stack up, and we need to carefully design the PCB stack up so that the signals which run from one IC to other, okay, the integrity is good. So we do extensive signal integrity simulations, and you look at these. This is typically a way an engineer looks at the link, and this is an eye diagram. So this we use it extensively to analyze how the link is performing. So if the eye is wide open, the link is good. And so that we spend enormous amount of time to design these links properly. And just to give you an example, there are like multiple 8 gigabit links running from one IC to other. And if we don't design these links properly, the eye diagram is bad, then we are in trouble here itself. Forget about radiating the signal. We are making bit errors right here itself. So this is one of the critical part of this design, which these students here in the labs do. Okay, so and then this is another, just to give you a glimpse of the kind of engineering challenges we face while designing such hardware. So there are like each such card has 24 different kind of power supplies, okay, and they need to come up in a particular sequence. And if they don't come up in a particular sequence, the ICs, the FPGAs will misbehave. So we have to design these power supplies on board accordingly. Okay, so that's an enormous task. Now, once the board, these were the two challenges which I briefly showed you. Now, once let's say the board has come, so you have to like test it, and these are the devices. Just an example of the kind of devices which are available on these boards. There are different kind of memories. There are these Ethernet switches. Then this is the optical interface. Then there's a PCI interface. And this I2C is to basically control different interfaces, UART, and we need to test all of them. Okay, so all that also we do. And there's something called board support. There's software, embedded software basically, so which contains operating system plus device drivers, and it allows the device to communicate with these devices on board, and all that is also developed in-house. Okay. So this is what this board support packages contain. We do that across different institutes, develop these kind of board support packages to test these boards and for these devices to communicate with each other. Okay, so that's what keeps going on in all these labs over here. And then, yes, the next, this is one part of the testing. So the second part of the testing is, like, let's say you want to physically test the board. So I mentioned that there is this PCI Express link. Okay? There are other links, 100G Ethernet, ECP links. So I just will tell you briefly about the problem we faced while testing one of these cards. So you see this is a PCI interface, and we need to plug this card into this. This is a motherboard, okay, because that's where this L2, L3 sit, and that's here the physical layer sits. Okay, so once we started testing this PCI interface, if people are familiar with this PCI interface, that's how it works. That there are different stages for this protocol to work: detection, polling, configuration, and data transfer. Okay, so when we started testing it, we realized that the PCI, this card was not even getting detected. And it took us month and a half to figure out the mistake we had done. And this was the only mistake we had done. The rest of the card was working fine. This is like 24-layer card. And what we realized was that we had shorted transmitter of this to transmitter of this, which should not have been done. And then we were stuck. But fortunately, before Corona stuck, we realized that there is only one vendor in the world which makes these kind of swap cables, which could swap transmitter to the receiver. And we could just get these cables on time, and we could test the card, and it's working fine. Okay, so these are the kind of problems we keep facing, and then, but fortunately we were able to resolve this. Okay, so this is how the work has been going on. And I'm like about to summarize this talk in another 2-3 slides. So I just thought I'll tell you what are the major systems that are being developed. So this is we are developing both sub-6 gigahertz massive MIMO remote radio head, and then there is this millimeter wave remote radio head. Okay, so this is fully digital. It can transmit 64 streams in practice, but we normally don't do that. So the number of streams is limited to 8. Then here, this is a millimeter wave system with 256 antennas. It's a hybrid system. Okay, this is a fully digital system. This is a hybrid system, and it can transmit 4 streams in parallel. Then we discussed about the baseband unit. So this can operate in standalone mode, and it can support both lower band and higher band. Then we are doing this 5G core network also from the scratch, and this is being done by one of the partner institute, IITs. Then we need to manage the whole test bed. Then there is a management layer being built for this test bed management. And then other paraphernalia which is being built across this test bed, and which I could not cover. The IoT, end-to-end IoT network using a mix of commercial and prototype components. And security is a very important aspect. So a lot of focus on security. Then Li-Fi. Then the other, which are the devices which are being, for these, we are using a mix of devices which are being developed, and some of them are being developed and some of them are commercially available. And this is a breakup of the 5G testbed work, which is being done across multiple institutes. And you will see that almost, I mean, there's so much of work happening across these institutes. So yes, and I'll conclude my talk that this is a test bed which is being built from scratch. Okay, so remote radio head hardware, software, core network, UE hardware and software, baseband unit hardware and software. Everything is being done in house with support from the startups, some of the from Indian startups. And then we do extreme hardware engineering design. We design multiple boards which have like 20 plus layers of 20 plus layers and multiple extremely high speed interfaces. Just to give you an example, the 64 RF transceiver, sub-6 gigahertz, fully digital hardware, millimeter wave RF transceivers, baseband units, everything is being done in-house. So extreme engineering, and most of that is done by the students in these institutes. Yes, we hire engineers, we take help from the companies, but most of the work is done by the engineers, by the students in the institute. Okay. So I'll just wrap up. This is the end of my talk. Thank you.